Hello everyone. Today I am going to explain my project, which is VGA Lane Hopper game. This project is designed using Verilog HDL and implemented on a FPGA board. The output of the game is displayed on a VGA monitor. The main objective of this project is to create a simple hardware-based game in which the player controls a frog and moves it across lanes while avoiding obstacles. The idea behind this project is to combine digital design concepts with a real time graphical application. Instead of only designing small individual circuits, this project shows how multiple hardware modules can be combined to build a complete interactive system. In this game, the player uses push buttons to move the frog in different directions, while obstacles move automatically on the screen. If the frog collides with any obstacle, the game detects it and shows a death condition. Let's dive into the code. Now I will explain the project module by module. First, let me start with the top module, which is top.v. In top.v, all the other modules are connected together. This file acts as the main integration block of the entire design. It takes the 100 MHz clock reset input and direction button inputs from the FPGA board. Then it passes these signals to the required modules and collects the final display output. Inside this module, VGA control is initiated to generate screen timing signals. The debounce modules are initiated for each button so that the input becomes stable. Then the pixel gen module is initiated to generate the game display and game behavior. After that, the RGB output is registered and sent to the VGA port. So, in simple words, top.v does not contain the full game logic by itself, but it connects all blocks and makes the complete system work together. Now, let us move to the next file, which is VGA controller.v. This module is responsible for generating the VGA timing signals required by the monitor. A video display needs proper synchronization signals to know when each row and each frame begin and end. This module creates the horizontal sync and the vertical sync signals and also generate the current pixel coordinates x and y. In the code, counters are used to count the horizontal pixels and vertical lines. The horizontal counter moves across one row, and when the row is completed, the vertical counter moves to the next line. A pixel tick is also generated from the 100 MHz clock so that the screen runs at the correct VGA speed. Because of these counters and timing signals, the system allows knows which pixel is currently being drawn. That is how the game logic can place the frog lanes and obstacles at the correct position on the screen. Now I will explain btn debounce.v. This module is used for button debouncing. Whenever a mechanical button is pressed, it does not produce one clean signal immediately. Instead, it may create small unwanted transitions because of contact bounce. If you use the raw signal directly, the frog may move incorrectly or more than once. In this code, the input button is first synchronized with the clock, then a counter checks whether the button value remains stable for a fixed amount of time. Only after the signal stays stable, the output is updated. Now the module makes sure that every button press is clean and reliable, which is very important for smooth game control. Now let us move to the main game module, which is pixelgen.v. This is the most important module in the project because it contains both the game logic and the drawing logic. First, this module stores the position of the frog using registers. When the player presses up, down, left, or right, the frog position is updated accordingly. The module also checks boundary conditions so that the frog does not move outside the allowed game area. Next, obstacle positions are also stored in registers. Different lanes have different moving objects, such as cars, trucks, and rocks. Their positions are updated frame by frame, and when an object reaches the edge of the screen, it wraps around and starts again from the other side. This module also contains the collision detection logic. That code continuously compares the frog coordinates with the obstacle coordinates. If both overlap, the module identifies it as a collision and activates the death animation and reset behavior. Another important part in the file is the score logic. When the frog moves forward, the score increases. The score is then converted into visible digits and displayed on the top of the screen. This module also includes the start animation and death animation. At the beginning, the game briefly shows the start effect. And when the frog dies, a death effect is displayed before the resetting the game. Finally, this file decodes the RGB color value for each pixel using the current X and Y pixel position from a VGA controller. It checks whether the pixel belongs to the frog, obstacle, wall, lane, divider, score, or text. Based on that condition, it assigns the correct color. So, pixelgen.v is called the heart of the project because it controls movement, collision, animation, score, and screen drawing all in one place. Now, I will move to the frog sprite files, which are nothing but here frog up.rom, frog down.rom, frog left rom.v, frog right rom.v. These modules are ROM based sprite memory files. Their purpose is to store the frog image pattern for each movement direction. In code, each ROM module takes a row and column value as input and gives the corresponding color data as output. That means for small pixel inside the frog image, the ROM already stores what color should be shown. So when the frog changes direction, the system selects the correct ROM module and displays the matching frog image. For example, if the frog moves upward, frog up.rom is used. If the file if the frog moves left, then frog left rom.v is selected. Because of the ROM files, the frog does not appear as a simple square block. Instead, it appears as a proper character sprite facing correct direction, which improves the visual quality of the game. Now, let us move to the constraint file, which is xtc.file. Uh, Here it is. This file is not a Verilog code, but it's still a very important part of the project. The constraint file is used to connect the logical ports in the code to the actual physical pins of the FPGA board. In this file, the 100 MHz clock pin is assigned first. Then the rest and direction buttons are mapped to their respective FPGA pins. After that, all the VGA output signals, including the 12-bit RGB lines, H-sync and V-sync, are mapped to the VGA connector pins. This file also set the IO standard, which is this case is LVCMO 533, and it defines the clock timing using the create clock command. So in simple words, the .xtc file acts like a bridge between the Verilog design and the actual FPGA hardware. Without this file, the code may compile, but the FPGA would not know which physical pin should be used for clock buttons and VGA output. Now, let me conclude the project explanation. Overall, this project is divided into different files, and each file has a specific purpose. The top module connects everything. Um, the VGA control generates display timing. The debones module stabilizes the button inputs, and the pixel generation handle the main game behavior and screen drawing. The ROM file store the frog images, and the constraint file connects the design to the FPGA hardware pins. All these files work together to create the complete VGA lane Hopper game on FPGA board, which we are using basis 3 board. This project gave me practical knowledge of both hardware design and VGA basic graphics implementation. Now I will move to the demonstration part of the project using the Basis 3 FPGA board. In the demo, I will show how the game runs on hardware, how the buttons controls the frog movement, and how the VGA output is displayed in real time. Now I am showing the controls on the Basis 3 board. First, this button moves the frog forward. Next, this button moves it to the right. Then this button moves it to the left. This button moves the frog downward. And finally, this is the reset button which restarts the game. Now I am demonstrating the reset button. When I am pressing the reset button, the game returns to its initial state. The frog goes back to the starting position and the game starts again from the beginning. Now I am showing the gameplay of the VGA Lane Hopper game. Here I am controlling the frog using the buttons on the Basis 3 board. The objective is simple. We have to move across the lanes while avoiding the moving obstacles. As the frog moves forward safely, the score increases. If the frog touches any obstacle, the game detects the collision and resets after the death animation. So this is the final output of my VGA Lane Hopper game project. As we can see, the game is working successfully on the Basis 3 board with VGA display output, smooth player movement, obstacle motion, score display, and rest functionality. This completes the project demonstration. Thank you for watching.